Welcome to the You Can Do video on lasers. The word laser stands for light amplification by stimulated emission of radiation. The laser device amplifies the light and produces an intense beam of light as a result of the atoms being stimulated. Basically speaking, a laser is a device which generates a coherent electromagnetic radiation in or near the visible part of the light spectrum. The laser action will occur in many different materials, and the laser process can occur in many different ways. Lasers may be classified in the following categories: chemical, gas, liquid, semiconductor, and solid materials. As you will soon see, lasers are used in many different applications. They're used in communicating devices. These are typically low-power devices which emit a visible light beam and are normally used for short-range communications requirements. Lasers are used for barcode scanning and as reading devices for digitally encoded information, commonly found on CD records and compact discs used in computers. Lasers are also used in fiber optic communication systems as a means of producing the data to be transmitted through the fiber cable. Lasers are also used as measuring devices. These are used to measure distances and velocities. By measuring the length of time it takes for a light beam to reflect back from an object being struck by a pulsed laser beam, the distance or the velocity of the object can be measured. Lasers are also commonly being used in medical surgical procedures. Lasers are being used for everything from removing birthmarks to removing cataracts from within the eye to making incisions for surgery. High-power lasers are used for welding and cutting applications. These style lasers are typically a CO2 gas device and can generate several thousand watts of power. CO2 gas lasers are extremely dangerous and proper safety precautions must be followed when working on these devices. Before proceeding into the subject of laser theory, you must first be knowledgeable of the safety precautions which are to be used when operating or working on any type of laser device. First, never look into a laser device when the power is turned on. Even at very low power outputs, the laser will cause damage to your eyes. Second, never point a laser beam at anyone. Medium and high power lasers will burn through the human flesh. Exposure of any part of the skin to a direct laser beam or reflections of the beam off reflective surfaces can cause severe skin burns and eye damage. Third, never shine a laser beam on a reflective surface unless the surface is designed for this purpose. Since the laser beam is a concentrated form of light energy, it will reflect off most materials. Fourth, always wear proper eye protection and clothing when working on the laser device. Fifth, never point the laser beam at flammable or combustible materials. Even reflections of the beam at sufficient power can start fires. Sixth, most laser devices use very high voltages which can be fatal. Always use proper handling for all high-voltage laser power supplies. 7. When building a laser system from a kit or working on a laser system, always follow the manufacturer's safety precautions included with the laser data. These safety precautions are provided for your protection. Now let's examine laser theory. As was mentioned earlier, laser stands for light amplification by stimulated emission of radiation. This intense form of light energy has several unusual and useful properties. To start with, laser light energy is monochromatic. A monochromatic light is a light which consists of just one wavelength. To illustrate this, we will use a flashlight and shine it on a crystal prism. As you can see, as the light passes through the prism, it is separated into its various wavelengths. Depending upon the light source used, a rainbow of colors will be seen exiting the crystal prism. When a laser beam is shined on the same crystal prism, the only light exiting the prism will be the frequency of the laser light beam. Since the laser light beam consists of a single wavelength, its light energy cannot be separated. As you can see from the simple illustration, the conventional light source uses a variety of wavelengths to produce its source of light, thus the rainbow effect. The laser beam, on the other hand, is not separated since it only consists of a single wavelength. Laser light is also coherent. This means that all the frequencies of the single wavelength of the light energy beam are in phase with one another. Since the wavelengths are all in phase, they will tend to stay together for a much longer distance. Natural light and most artificial light sources will produce an incoherent beam of light. This incoherent beam of light consists of several wavelengths of energy which are placed randomly together. Since the wavelengths are not uniform, they will tend to diverge or spread out as the light beam gets further away from its source. Because of its properties of being monochromatic and coherent, the laser light beam is able to possess a great deal of energy. This energy will remain in its concentrated form for greater distances. A laser beam the size of a pencil, with the use of proper optics, will only spread to a diameter of approximately 1.5 miles between the Earth and the Moon. When you consider the distance between the Earth and the Moon, about 250,000 miles, this is a very impressive feat. To comprehend how this intense beam of light is produced, we need to understand exactly how a laser works. Before proceeding with how a laser device works, we will pause for a short review of the material just discussed. A laser is a device which produces a coherent electromagnetic radiation in or near the visible part of the light spectrum. There are many types of substances used to generate the stimulated emission of radiation. Some of these substances include chemical, gas, liquid, semiconductor, and solid materials. Lasers are used for communication purposes, scanning and reading data, as measuring devices, for cutting and welding, and for many medical procedures. When working on or using laser devices, always follow all safety precautions. Never look into the beam of a laser, no matter how small the power output is. Never point a laser at anyone. Even though very low power lasers will not damage the skin, you should not make it a habit of aiming a laser at yourself or other people. Do not aim a laser at a reflective surface. Due to the characteristics of a laser beam, it will reflect off most surfaces. Always wear proper eye protection designed for the laser system you are using. Never aim a laser beam at flammable or combustible materials. Always use extreme caution when working on the high voltage section of any laser device. Always follow all manufacturer safety precautions when working on or using any laser device. A monochromatic light is a light which consists of a single frequency. A coherent light is a light which is a single frequency and all the light energy is in phase with itself. This concludes review number 1. At this time, you should stop the video and complete section A in your student workbook. In this part of the video, we will examine how a laser device is able to produce a monochromatic, coherent beam of light energy. As you learned earlier, a laser produces a stimulated emission of radiation. This process of stimulated emission is what makes the laser energy different from man-made and natural light sources. Stimulated emission occurs when an atom or molecule absorbs excess energy and holds this excess energy until it is stimulated by an external energy source, such as a photon at the proper wavelength or an electron. When the atom or molecule is stimulated, it emits its held energy in the form of light. This process of stimulated emission makes the light energy being produced by the laser device different from the light produced by natural or man-made devices. Visible light energy produced by the sun or man-made devices is a result of spontaneous emission which occurs when the atoms or molecules lose excess energy without the need of an external stimulating energy source. To better understand how a laser device works, let's first examine an atom and its associated energy levels. Here you see a helium atom. It consists of 2 electrons orbiting around a nucleus of 2 protons and some neutrons. The process of stimulated emission of radiation occurs the same way in the helium atom as it does in other basic laser materials. Therefore, the principles shown to you with the use of the helium atom will apply to the other laser substances as well. All atoms contain spherical shells which encircle the nucleus. These shells are where the electrons exist and orbit around the nucleus. An atom in its uncharged state will contain the same number of electrons in the spherical shell as it does protons in its nucleus. That is why the helium atom contains 2 electrons and 2 protons. A certain amount of energy, which is strictly defined by nature, is required to hold an electron in its orbiting shell. The further away the electron is from the nucleus, the more energy it requires to hold this electron in its orbit. In its lowest natural orbit, the electron is said to be in its ground state. When a precise amount of energy is added to the orbiting electron, it can be forced to jump to the next spherical shell. When this occurs, the atom is said to be excited. An atom will remain in this excited state for a period of milliseconds to microseconds. It then returns to its normal ground state. In 1911, a Danish physicist by the name of Niels Bohr provided us with the theory that atoms lose energy or emit energy when the electrons orbiting the nucleus move from a higher energy orbit to a lower energy orbit. This theory was further built upon in 1917 by Albert Einstein when he suggested that an atom or molecule could be stimulated to emit light energy at a particular wavelength when an external energy source of that particular wavelength reached the atom or molecule. This was the birth of stimulated emission. According to the theory of Niels Bohr, the atom will only emit energy when the electron orbiting the nucleus moves from a higher energy orbit to a lower energy orbit. Therefore, for laser action to occur, the atom must first be excited by causing one or more of the orbiting electrons to jump to the next higher energy level. This can only be accomplished by causing the orbiting electrons to absorb energy from an external source. The 2 most common sources of this external energy are photons and electrons. The photon is a form of electromagnetic radiation and may be thought of as an energy in transit. This transit energy is made up of extremely high velocity particles, or packets of energy waves. In the field of optical energy, these high velocity packets of energy are called photons. The shorter the wavelength of the photon, the more energy it will contain. Now let's see what happens when an atom absorbs energy. When an electron acquires more energy than is contained in the electron's normal orbiting shell, it will cause the electron to jump to the next higher energy level. The atom is then said to be excited. Since this excited state is unstable, the electron will quickly return to its normal orbiting shell. When it does, the electron will release the absorbed energy in the form of a photon or particle of light. The wavelength of this photon will be typical of the material in which the transition occurred. Under normal conditions, the majority of orbiting electrons will remain in the lower orbital rings or energy levels of the atom. When the atom becomes excited by an external energy source, the orbiting electron will move from the lower energy level to the next higher energy level. When this occurs, it is called population inversion. The spontaneous emission of photons when an electron moves from a higher energy level to a lower energy level is where laser light begins. To maintain the stimulated emission of photon energy requires that you gather as many excited atoms together in one substance as you can. The excited atoms, however, must be of the same type of material. When you have acquired enough excited atoms together in one substance, spontaneous emission of photons will occur as the electrons in the excited atoms undergo the transition from the excited state to the ground state. When this occurs, an interesting phenomenon happens. When one of the emitted photons strikes an atom which is already excited, it will cause this excited atom to emit a photon of its own. Thus, there are now two photons where there was previously just one. These two photons then continue to go on and strike more excited atoms. Each time a new excited atom is struck, a new photon is generated. This process of photons generating other photons is referred to as stimulated emission. One thing that you should bear in mind is that a photon of a particular wavelength can only generate another photon of the same wavelength. Therefore, a laser is said to be monochromatic, since its photon, or light energy source, is a single frequency. The laser beam is also said to be coherent, since all the light particles are in phase. The coherency of the beam is a result of the process of the stimulated emission. Because the energy of the laser beam is of a single frequency, and the light particles are in phase, it produces a much more powerful and intense beam of light energy than is available from an ordinary incoherent light source. These characteristics of the laser beam cause the photon energy packets to travel in parallel with one another. The divergence of the laser beam is only about 1/20th of a degree, which means that the light particles do not scatter or diffuse appreciably over long distances. You have seen a very simplified description of the process required to stimulate an atom into the emission of photon particles. However, this description should serve as a foundation from which you can build upon to further your understanding of how laser light energy is produced. At this time, we will pause for a short review of the material just discussed. An electron in its lowest natural orbit is said to be in its ground state. By applying a precise amount of energy to the orbiting electron, the electron can be made to jump to its next higher orbital shell. When this happens, the electron is said to be in its excited state. The atom will only maintain this excited condition for a period of milliseconds to microseconds. When the electron moves from its excited orbit to its normal orbit, it will emit a burst of energy called a photon. The photon is made up of extremely high velocity particles of energy waves. When a photon strikes an excited atom, two photons will be generated. A photon of a particular wavelength can only generate another photon of the same wavelength. This concludes review number 2. At this time, you should stop the video and complete section B in your student workbook. In this part of the video, we will discuss basic laser systems and how they work. Only 3 components are necessary for laser action to take place. There must be a lasing medium, a pumping system to supply the energy to the lasing medium, and a resonant optical cavity. There are several solid, liquid, and gas materials available to be used as the lasing medium. As long as the material contains atoms which can achieve one energy level change and can maintain this level long enough for the population inversion to take place, the material will work as a suitable lasing medium. Even though only one energy level change is required for stimulated emission between the next higher orbital shell and the ground state to take place, many laser systems will use more than one energy level change and can simultaneously operate on many different wavelengths. As you will see, this is the case with the CO2 gas laser. The energy source used to establish stimulated emission is often referred to as pumping. Pumping is accomplished by means of optical, electrical, chemical, or nuclear methods. The pumping system must supply sufficient energy to the lasing material to enable it to excite enough atoms to energy levels sufficient to achieve population inversion. As you recall, population inversion must take place before lasing action will occur. The least complicated pumping method is optical pumping. Optical pumping is the use of photons as the means of exciting the atoms. Optical pumping is generally achieved by flash tubes or other lasers. Electron pumping is achieved by passing an electric current through the lasing material. The gas laser often uses electron pumping. As the electric current passes through the gas medium, it excites the gas molecules to the state of population inversion, which in turn creates the stimulated emission at the strength necessary to obtain the laser beam output. The third part of the laser system was the resonant optical cavity. The resonant optical cavity is formed by mirrors at each end of the cavity which bounce the energy back and forth in a precise, regulated fashion. The optical cavity actually amplifies the stimulated emission through the process of reflecting the photons through the lasing medium. With each pass of the photons through the lasing medium, the number of new photons being generated will increase. Now that you know what the parts are that are required for a basic laser system, let's examine some typical laser devices. We will begin with the ruby rod laser. The heart of the ruby rod laser is in its synthetic composition. The basic chemical composition of the ruby rod crystal is aluminum oxide and chromium. Only the chromium atoms are used for the purpose of stimulated emission of the photons. Both ends of the ruby crystal are polished flat, smooth, and parallel. A silver coating is also applied to both ends of the synthetic laser crystal. One end, the rear of the ruby rod, will be coated to the point of total reflectiveness. In other words, it will reflect 100% of the photon energy being generated within the rod. The other end, or the front end, will only be partially reflective so that a small percentage of the laser beam can escape from the rod. The partially reflective end will only allow approximately 4 to 8% of the laser light to escape through the coated surface. Here you see a typical ruby rod laser. Notice that it consists of a ruby rod which is surrounded by a quartz helical lamp. The helical lamp is basically a flash tube. The operation of the helical lamp is very similar to that of the electronic flash used by today's modern cameras. When the flash tube is energized, the synthetic ruby rod absorbs a portion of the energy produced by the quartz lamp. This energy is actually absorbed by the chromium atoms. As the chromium atoms absorb the energy, the electrons encircling the atoms will move to the next higher orbital plane. This places the atoms in an excited state. As you learned earlier, the atoms will only maintain this excited state for a period of milliseconds to microseconds, then they must return to their ground state. When this happens, photon energy is emitted from the chromium atoms. The photon energy, which is created in the ruby crystal, then begins to bounce back and forth from one end of the ruby rod to the other. As the photons travel from one end to the other, they collide with other excited atoms, which in turn create even more photons. This process of reflecting from one end to the other continues until the light energy is sufficient to escape through the front end of the laser crystal. Due to the fact that the ruby rod must be pumped with energy by means of the flash lamp, the ruby rod laser will produce pulses of laser light. Operating the ruby laser in a continuous mode is very difficult, since this would mean that the flash tube would also need to be operated in a continuous fashion as well. The majority of the energy being produced by the flash lamp is dissipated as heat. This buildup of heat would eventually cause the ruby crystal to overheat and lose power. For continuous operation, a different type of active laser material would be required. Here you see a gas laser commonly referred to as the HeNe. HeNe stands for helium neon, which is the active lasing medium in the laser device. The typical HeNe laser is a sausage-shaped glass tube which contains two mirrors placed at each end of the glass enclosure and is filled with a helium neon gas mixture. An anode is generally placed inside the tube near the rear mirror. A cathode is generally placed inside the glass enclosure near the front end of the tube. The resonant cavity is the area between the front mirror and the rear mirror. The HeNe device will also generally contain an output optical lens, which is mounted on the front end of the tube just beyond the front mirror. Bear in mind that the HeNe device is actually a vacuum tube, and its operation is very similar to that of a standard diode vacuum tube, in that the current will flow from the cathode to the anode. The vacuum inside the HeNe device will typically place the total pressure somewhere in the neighborhood of 3 to 20 torr. The helium is the prominent gas in the HeNe device. There is typically 8 times more helium than neon in the vacuum tube laser device. The most common wavelength of the HeNe laser is 632.8 nanometer. The 632.8 nanometer wavelength produces a visible red light. HeNes are also available in infrared, yellow, green, and orange wavelengths. However, for most purposes, the standard HeNe device will be the red-emitting laser. As you will see, the operation of the HeNe device is similar to other laser devices. When the laser is first activated or turned on, the HeNe tube receives an initial ignition pulse of 10,000 volts, which breaks down the gas molecules and starts the laser operation. When the gas becomes ionized, the HeNe tube will conduct a current flow of only a few milliampere and maintain a voltage of 1,000 to 2,000 volts. The electrons in this discharge path will raise both the helium and the neon atoms to their excited states. The more abundant helium atoms will absorb most of the energy and then transfer this energy to the neon atoms. Since the neon atoms are excited at about the same energy level as the helium atoms, when the transfer of energy occurs, the neon atoms drop to a lower metastable level, thus producing the laser energy. When current is passed between the electrodes at opposite ends of the tube, the gas molecules become excited and produce the population inversion required for the laser action to occur. The photons resonate between the rear mirror and the front mirror until the energy is sufficient to overcome the reflectiveness of the front mirror. On the average, only about 1% of the light energy will emerge from the front mirror of the device. Here you see the top view of a CO2 gas laser. The CO2 gas laser is generally a high-power lasing device and is used quite frequently in industrial applications for such uses as cutting and welding. The CO2 gas laser uses a mixture of gases consisting of oxygen, nitrogen, helium, and carbon dioxide. Since heat is an undesirable byproduct of the lasing action of this type of laser, it almost always contains a heat exchange system to remove the excess heat. The CO2 gas laser also contains a separate gas supply system and a blower motor. The gas supply system is used to supply a continuous flow of fresh gas to the laser device. The blower motor is used to circulate these gases within the cavity. Notice that there is also a vacuum pump, which is used to maintain the proper torr level within the laser cavity. As you recall, the laser operates like a vacuum tube. Therefore, it must operate in a state of controlled vacuum. The CO2 gas laser will generally contain a series of mirrors in the optical cavity. There will be a rear mirror, 2 or more folding mirrors, and an output mirror. The output mirror is often referred to as an output coupler. The rear mirror and the folding mirrors will be 100% reflective, while the output coupling optic will be about 96% reflective. Notice that the beam originates off the rear mirror, then reflects off the 2 folding mirrors, then exits the output coupler. The purpose of the folding mirrors is to force the photons to pass through the excited gas molecules, thereby increasing the strength of the laser beam. The folding mirrors, in effect, allow more power to be generated from a shorter cavity laser. If the beam is folded 3 times, the power output from the laser would be the same as a laser which had a cavity 3 times longer. Since the CO2 gas laser operates in a continuous mode, it will almost always contain a shutter device which is used to control the output of the laser beam. The shutter is water-cooled and is electrically opened when the beam is required. When the beam is not required, the shutter will remain closed and the energy from the beam will be dissipated in the form of heat on the shutter device. Large industrial CO2 gas lasers will generally contain more than one anode for the purpose of maintaining an even discharge between the cathode to the anodes. By spreading out the electrical discharge over a wider area, a more even excitation of molecules may be obtained. Now let's see how the CO2 gas laser generates its beam. When the CO2 gas laser system is energized, the electrical discharge between the cathode to the anodes will cause the nitrogen molecules to become excited. This upper vibration energy from the nitrogen is then transferred to the carbon dioxide molecules through the means of collisions from the photons being emitted from the nitrogen atoms. As the energy is transferred to the carbon dioxide atoms, they become excited as well. When the energy from the CO2 atoms falls to 2 lower levels, they emit photons at wavelengths of 9.6 microns and 10.6 microns in the process. Once the electrons have fallen to their ground state, they become excited again, and the process starts all over. The helium gas is used to assist in the cooling process of the gas mixture. This cooling process improves the laser's efficiency by increasing the rate at which the CO2 molecules relax from their excited state to their ground state. The laser action begins when the photons are emitted and they move in a precise alignment with the mirrors inside the laser cavity. As the photons reflect from one mirror to the other, they stimulate even more photons with each pass through the cavity. This process of photons creating more photons quickly builds up to an intense coherent optical energy at a wavelength of 10.6 microns. Caution should always be observed when working on or near a CO2 gas laser due to the fact that the optical energy being emitted from one of these devices is in the infrared region and cannot be seen by the human eye. We will now pause for a short review of the material just discussed. Any molecule which can achieve population inversion will work as a suitable material for the lasing medium. Many lasers use more than one energy level change and can operate on different wavelengths. The energy source used to establish stimulated emission is often referred to as pumping. Optical pumping is the use of photons as the means of exciting the atoms into their higher energy levels. Electron pumping is achieved by passing an electric current through the lasing material. The resonant optical cavity is formed by mirrors placed at each end of the laser cavity. At least one of the mirrors will be 100% reflective, and the other mirror will be 96 to 98% reflective. The optical cavity amplifies the stimulated emission through the process of reflecting the photons through the lasing medium. ruby rod is pumped with energy through the use of a flash lamp. The lasing medium in a He laser is helium and neon. The helium is the prominent gas. The most common wavelength of the He laser is 632.8 nanometer. This wavelength produces a red, coherent beam of light energy. CO2 gas lasers are generally high-power lasing devices. These type of lasers will emit an infrared beam of laser light, which cannot be seen by the human eye. This concludes review number 3. At this time, you should stop the video and complete section C in your student workbook. In this portion of the video, you will learn about laser diodes and how they work. The laser diode is a semiconductor device designed to emit a coherent beam of light energy. Power outputs from these devices are typically about 3 to 5 milliwatt. The characteristics of the laser diode are determined by its chemical composition and its geometry. All laser diodes are essentially multi-layered in structure and are made of several different types of semiconductor materials. The various semiconductor materials are doped with impurities to form the P and N substances required for fabrication of the diode. The structure of the laser diode being shown to you now is very similar to many found in today's market. The base of the diode is doped very heavily with N-type impurities. The cladding portion of the diode being shown is also doped with N-type impurities, however not as heavily. Half of the active layer will either be completely undoped or very lightly doped with N-type impurities. The other half of the active layer will be lightly doped with P-type impurities or will contain no dopant at all. The next cladding layer will be lightly doped with P-type impurities. And the final top substrate layer will be heavily doped with the P-type impurities. This substrate layer actually acts as a cap for the semiconductor device. You should also notice that the metallic plates are grown on each of the substrates. These metallic plates are used as the connecting points for the semiconductor device. The ends of the semiconductor crystal are called facets. The rear facet is coated with a reflective layer, which is designed to reflect 100% of the light back into the active layer of the laser diode. The front facet is highly polished and may or may not have a very thin layer of reflective coating applied. When the current passes through the metallic plates, the excess electrons in the N-type material combine with the holes in the P-type material. This recombination of charge carriers takes place in the active area of the semiconductor device. When the electrons in the holes recombine in the active region, the atoms are induced into an excited state of population inversion. Thus, the lasing process begins. The photon energy begins to reflect back and forth from one end of the waveguide to the other. As the photons collide with other excited atoms, more photons are created. The photons continue this back and forth cycle until the photon energy is amplified into a coherent beam of energy. Once the photons are sufficient to overcome any losses due to the absorption and scattering, the laser beam will exit the front facet of the laser device. The beam of light emerging from the front of the laser device will form a vertical ellipse. By now, you should have a basic understanding of the theory of how laser light energy is produced. You have seen that laser light energy is monochromatic as well as coherent. You have also learned that all basic laser systems must have 3 primary elements. These are a lasing medium, an optical cavity, and an energy source capable of activating the molecules into a state of excitation. You have also examined the ruby rod laser, gas lasers, and the semiconductor laser devices. At this time, we will briefly cover some of the uses of these laser devices. We will begin with the simple laser pointer. Here you see a typical laser pointing device. These laser devices are frequently used in sales meetings, seminars, classroom instructions, or any place where a person needs to point out a particular point of interest. Inside the laser device, you will see the laser diode, a small printed circuit board which contains the control circuitry for the laser device, a push button to turn the device on, and 2 batteries. The batteries, of course, are the power source for the laser pointer. Now let's examine another familiar device. Here you see a barcode scanner. The barcode scanner is used in almost all retail outlets and is used to scan the price of the product into the computer where a multitude of functions takes place. The price of the product is totaled so you know how much to pay, and the product is removed from the inventory so the store knows when to order more. Inside the barcode scanner, you will see the laser device, which may be a Heine gas laser or a semiconductor laser as shown here. You'll find a set of optics which will contain a lens and a focus lens. The larger lens is used to focus the returned beam back onto the photodetector. The focus lens is used to maintain the correct beam size for the scanning purpose. There's also an oscillating mirror which is used to automatically move the beam of light across the barcode symbols. Notice that there is also a photodetector. The photodetector is used to read the information being reflected back from the barcode symbol. The barcode scanner will also contain a printed circuit board so that the returned information can be processed. The operation of the barcode device is very simple. It illuminates the barcode symbol with a narrow beam of light which rapidly moves back and forth across the pattern. The laser beam will scan at a rate of 40 scans per second or more. As the beam strikes the dark bars and the white spaces, it reflects back into the window of the device, bounces off the oscillating mirror into the larger lens, and is then focused back into a narrower beam to be detected by the photodetector. The photodetector then converts these variations of the reflected beam into a series of digital pulses, which is then fed into the computer for further processing. At this time, we will pause for a short review of the material just discussed. The laser diode is essentially a multi-layered semiconductor device which contains an active region where the P and N materials join together. The ends of the semiconductor device are called facets. The rear facet will be highly polished and will have a coating to reflect 100% of the stimulated emission of photons within the active region. The front facet will also be highly polished, but it may or may not have a reflective coating applied. Laser pointing devices are typically very low power and are used primarily by speakers, instructors, and others who find it useful to direct attention to visual aids and to other topics being discussed. The barcode scanner uses either a Heine laser device or the semiconductor laser device. Both are in common use and operate on the same principles. Since the beam must be scanned across the barcode pattern to effectively read the data, an oscillating mirror is placed inside the scanning device. The reflected beam is seen by a photodetector device located inside the barcode scanner. The light beam is then converted into a digital pulse train, where it is then fed into a computer system for further processing. This concludes review number 4. At this time, you should stop the video and complete section D in your student workbook. In this portion of the video, we will discuss the read operation of a typical CD memory device. To fully understand the CD memory system and how it is used in the retrieval process of information, we will first examine a standard CD disk. The compact disc, or CD as it is more often called, is a mass storage device which yields its information through the use of laser technology. Today's laser devices are so precise and produce such a small beam size that a disc of approximately 5 inches in diameter can store as much as 650 megabytes of information. This is several hundred times more than is available from a typical 3.5-inch floppy disk, which uses a magnetic storage medium. The CD is a very durable storage device. It is impervious to heat, humidity, fingerprints, magnets, or even head crashes, which are common problems in floppy and hard drive systems. Here you see what the information looks like on a standard pre-recorded CD. Notice that it resembles parallel lines of evenly spaced protrusions. Each of these protrusions is approximately 0.6 micron in width. The flat area in between the protrusions is called the land. When the focused laser beam strikes the flat surface, or land, between the protrusions, most of the light energy is reflected back to the detector circuit in the drive assembly. At the point where the laser beam strikes the disk, the beam size is approximately 1 micron in diameter. This diameter is a little larger than the wavelength of the laser light. In theory, this is as small as the beam can become. When the focused laser beam strikes a protrusion, much of the laser light energy is scattered sideways. This leaves very little to be reflected back to the detector device. Each time the laser beam moves from a land to a protrusion, or from a protrusion to a land, the reflected light energy changes in intensity. The detector circuit distinguishes this change in intensity and produces a series of digital pulses which represent the data being retrieved from the disk. Now that you have a basic understanding of the compact disc itself, let's examine how a standard compact disc system reads the information from the CD. Here you see the read part of a typical optical disk drive system. Even though there are variations in design of the various optical disk drives, they must all contain the basic components shown to you in the simplified diagram. Notice that at the bottom of this optical read system, you will find a semiconductor laser device. These lasers are generally aluminum gallium arsenide devices which operate in the infrared wavelength. Here you see the collimator lens. The purpose of the collimator lens is to ensure that the electromagnetic waves of light energy are in parallel. When the laser diode emits its monochromatic coherent beam of light energy, the beam will diverge or spread out over a given distance. In other words, the laser light energy waves are not in parallel. When the diverged beam passes through the collimator lens, the rays of light energy are forced to travel in parallel with one another. Here you see the polarization beam splitter. This optical component contains some very unique characteristics which take advantage of the light energy which is produced by the infrared laser device. The light wave energy produced by the semiconductor laser diode is such that all the in-phase wavelengths of the light wave vibrate in one direction or on the same plane. This is called polarization. If you could look into the end of a polarized light beam, you would see that the electromagnetic fields were all in parallel lines. Three forms of polarized light energy are used in the optical disk drive system. Horizontal polarized light energy is produced by the laser diode. The horizontally polarized light energy is then converted into circular polarized light energy. And the circular polarized light energy is then converted into vertically polarized light energy. The polarization beam splitter allows the horizontally polarized light energy to pass through unobstructed, while at the same time blocking the vertically polarized light rays. These blocked light rays are then reflected through the side of this optical device. Here you see another optical lens called a quarter wave plate. The purpose of this lens is to slow the horizontally polarized light energy to the point that the light waves begin to rotate or spin in a circular motion. When this rotating polarization becomes uniform, it is called circular polarization. This circular polarized light energy will complete one rotation for every cycle of the light wave and will maintain a constant angular speed. Next, you see an optical device called an objective lens. This lens is used to converge or focus the laser light energy to the proper size and shape necessary for the reading of the data contained on the compact disc. Here you see the converging lens. It is another form of focusing lens, which is used to reduce the size of the returned laser beam containing the data received from the CD. Finally, we have the cylindrical lens. This is the last optical device in which the received light energy which contains the data must pass through before reaching the photodetector, which, as you already know, is used to convert the received light wave data into electrical pulses for further processing by the computer system. Now let's see how this system works. The infrared laser beam first passes through the collimating lens, where it is forced to travel in parallel. The beam then continues through the polarization beam splitter and into the quarter wave plate. The quarter wave plate takes the horizontally polarized beam of light energy and converts it into a circular polarization. The circular beam then continues into the objective lens, where it becomes focused onto the disc. The laser beam then reflects back down its original path to the quarter wave plate, where the circular polarized beam is converted into a vertically polarized beam of light energy. Since the vertically polarized beam cannot pass completely through the beam splitter, it is reflected through the side of the optical device. The reflected beam then passes through the converging lens and cylindrical lens to the photodetector device, where the light energy is converted into electrical pulses. As is shown here, the optical read device will generally be located below the compact disc. The compact disc will then spin above the disc reading system. We will now pause for a short review of the material just discussed. The compact disc is a mass storage device which yields its information through the use of laser technology. The data content of a pre-recorded CD resembles parallel lines of evenly spaced protrusions. The flat area between the protrusions is called the land. When the focused laser beam strikes the flat surface, or land, between the protrusions, most of the laser energy will be reflected back to the photodetector circuit. When the focused laser beam strikes a protrusion, much of the laser energy will become scattered, and very little will be reflected back to the photodetector circuit. An optical disk drive system will normally use an infrared semiconductor laser diode as the active data collecting component. The collimator lens is used to ensure that the electromagnetic waves of light energy travel in parallel with one another. The polarized beam splitter allows the horizontally polarized light waves to pass through unobstructed, while at the same time blocking the vertically polarized light waves. The quarter wave plate is used to convert the horizontally polarized light energy from the laser diode into circular polarized light energy, and then convert the reflected circular polarized beam, which contains the data, into the vertically polarized light energy. The objective lens is used to focus the laser beam energy to the proper size and shape necessary for the accurate retrieval of data from the compact disc. The converging lens and the cylindrical lens are the optics required to accurately focus the reflected light energy, which contains the data retrieved from the disc, onto the photodetector device. This concludes review number 5. At this time, you should stop the video and complete section E in your student workbook. So far in this video, you have learned how photon energy is produced and amplified to the point of becoming an intense beam of light energy. You have seen how the electrons in the molecules must become excited and produce a state of inverse population before the stimulated emission of radiation can occur. You have also learned about the 3 components required before laser action can take place. These were the lasing medium, a pumping system, and a resonant optical cavity. By now you should have a solid understanding of the working principles of 4 common laser devices: the ruby rod, HENI, CO2 gas laser, and the semiconductor laser devices. At one time, lasers only existed on the pages of science fiction, but now they are used on a daily basis around the globe. As a technician, you must learn this new technology to further your career in electronics. All that a person achieves, or all that they fail to achieve, is a direct result of their own education. As always, you should review this video often to retain your newly acquired knowledge.